Hey everybody, Mr. Smith here again. What we're going to do is today talk about the idea of voltage and specifically how we go about the business of connecting it with work and energy. So we're going to dive right in with a few examples. Here's a really easy one. This is taken from our lab, thanks to Brett who gave us his diagram. We had a parallel plate here of metal charged up at 7 volts. This one was connected to ground. And the question is asking us, what's the electric field inside of this parallel plate arrangement? So real quick, you should remember that lines that are equally spaced of constant voltage leads to lines that are equally spaced of electric field, and so constant electric field. And so this goes right back to the first definition we did when we talked about voltage. Where electric field is constant and distance is constant, then this is what voltage was. It was E times D. So we can flip this around backwards very easily, and we'll solve it for E. And if they want to know the electric field in between these two metal plates, all we have to do is just measure the distance between the plates. And we did. We got 10 centimeters, so we had 7 volts over 10 centimeters, and we get 70 volts per meter. All right, so super easy. This is one of the units you'll see on electric field. So second question is similar. Instead this time, what we're going to do is to allow a positive test charge. So here's a little positive Q, 1 microcoulomb, to zip between this positive plate and ground. And they're going to ask us how much work is done on that test charge as it moves from high to low potential. Well, here's the story. That was also part of this definition that we gave when we talked about voltage. So work was equal to Q times V, because V was equal to Ed. So you can use this one just the same. If they want to know that the work that was done, it's just going to be 1 microcoulomb times that potential difference of 7 volts. And that's going to give us the work that was done on our little test charge. So just multiply these two, and you're going to end up with 7 microjoules, or 7 times 10 to the minus 6 joules of work. Okay, so that's 2 easy ones out of the way. Now, the next one really is useful because often in physics too, what we do is we connect the small world of things like electrons with the big world of things like electric cars. So when we do that, we get examples like this one, where we're going to talk about a unit of energy that you may not have ever seen before. This is a thing called an electron volt. So here's how this question is staged. We have an electron that moves through a potential difference, and they want to talk about the kinetic energy that the electron gains. So here's 1 electron. You don't get any smaller than that. So what this electron is going to do is to zip upward along those electric field lines and gain kinetic energy as we let it zip. The reason we're going to use these units of EV sometimes is that the units in joules are really, really tiny, and sometimes they're awkward to talk about. So if we're going to stay on the level of the very small, we'll really stick in the units of EVs of energy. So what's an EV of energy? I'll show you. If I had work equals QV again, but instead I had 1 electron, and we just let that electron be the unit of charge, then our 7 volts right here times 1 electron would give us what we call 7 EVs of energy. Okay, so what's 7 EVs of energy really? Well, all you have to do is just say, if I put in what the electron really equals in coulombs, then we'll get our answer. So we get 1.6 times 10 to the negative 19 of those coulombs times our 7 volts, and we end up with an amount of work of 1.12 times 10 to the negative 18 joules. So here's the deal. There's a standard conversion factor that you're going to want to bank away. It's that 1 EV equals 1.6 times 10 to the negative 19 joules. And so that's your bridge between the micro world of electrons and the big world that we live in. Okay, so what's a typical reason you need that conversion? Well, it's one like this. If they ask us the velocity of that electron after it's done accelerating, the reason that voltage is so important to us is that it connects with the idea of energy. So here's a form of energy, kinetic energy. So we know that kinetic energy for an electron or a car is 1/2 mv squared. The units of m are going to be in kilograms, velocity is going to be in meters and seconds, and this is going to be in joules. So if I want to figure out the velocity of that electron, I better have the kinetic energy in joules. So I'm going to need to do that conversion. So I'll do my algebra first. We got 2 KEs over m, and we'll plug in our numbers. So square root of 2 times 1.12 times 10 to the negative 18 joules, and we'll divide it by the mass of the electron, which is really small, 9.1 times 10 to the negative 31 kilograms. And when we go ahead and pull the trigger on that, we'll figure out that the velocity of the electron, just had it here a second ago, is 1.57 times 10 to the 6, and that's in meters per second. Okay, so that's an example where you're going to bridge from the small world to the big world and how to do it. Now, getting towards the end here, finally, one of the reasons that we really like the idea of voltage is that it's really simple to deal with. It's so much simpler than electric field, and I'll give you an example of how. When we talked about electric fields, they followed the same rules for adding that forces did, meaning they were vectors. We had to pay attention to the I's and J's and K's, or the 25 newtons at 225 degrees, that kind of stuff. Because electric field times distance equals voltage, and because voltage is a vector, is a scalar rather, it becomes so easy to work with. We don't have to worry about the vector stuff. So here's an example. This was a hard example when we worked with force and when we worked with electric field. And let me show you how easy it is now. We've got 3 charges in something like the triangle of torture, but it becomes the triangle of trivia. What's the potential created by these guys in the vicinity of Q3? Well, here's how easy it is. We just isolate on this one, and we'll say the voltage created by 1 over here at 3 is going to be just K, Q1, so 4 microcoulombs, divided by the distance between the two of them, divided by 12 centimeters, or 0.12 meters. And you can do that math, and it turns out that that is equal to 300,000 volts. So this guy right here is going to set up a 300,000 volt potential down here. By the way, a microcoulomb is really big, isn't it? When you're 12 centimeters away from it, that's a little bit bigger even than our Van de Graaff generator in class can do. So part 2 of this question, what is charge 1 going to do out, charge 2 rather going to do out here by charge 3? It's so easy. It's going to be K times, this is the time I do use the minus signs. Why? Because there's no vectors involved. There's nothing that's going to mess you up here, so it's totally sensible, in my opinion, to use minus signs where they give them to you. And so here's 0.104 meters. So we have a bigger charge, a shorter distance, and this one's going to be a bigger voltage. So it's something like negative 693,000 volts. And what's the total potential in the vicinity of charge Q3? It's just this easy. All you do is add the voltages. And so the voltage at charge 3 is just going to be the sum of these two. So it's, I get negative 393,000, or negative 393 kilovolts. Okay? So there you go. Those are all the basics. And what we'll do is work on them more in class, but you have everything you need to get rolling. So take care. Bring your questions to class. Good to see you, and take care. Bye-bye.